Hello student. In last video we have discussed about a derivation of capacitance of parallel plate capacitor, right? So we have derived equation for capacitance. So what was that equation? C is equal to A epsilon naught divided by D. What was A? A was the area of plate, area of the capacitor plate, right? There are two plates having same area. So A is the area and epsilon naught is the relative permeability, right, of a medium. Then D is the distance between two parallel plate, right? So if the question was asked like the factors affected by parallel plate capacitance, factors affected by parallel plate capacitance means what answer you have to write? You have to consider that equation plus first, right? For parallel plate capacitance, C is equal to A epsilon naught divided by D. Now from this equation what you will get? What you will get? Parallel plate capacitance is directly proportional to area of the plate, right, and inversely proportional to the separation between two plates. These two are the factors affected by parallel plate capacitance, right? And today we will discuss combinations of capacitor, right? Today we will discuss combinations of capacitor. There are two types of combinations. One is parallel combination, right? Another one is series combination. Means what? Now two or more capacitors are connected in two ways here. One is either in series combination or in parallel combination. Now in this combination concept we have to discuss about their capacitance. If three capacitors are connected in series means how we will see in the diagram now, right? If three capacitors are connected in series, then what is the total capacitance of all those three capacitors? We have to calculate. So we have to check out total equivalent capacitance of a system in which capacitors are connected in series. Same way we have to discuss about parallel also, right? So today we will discuss series combination of a capacitor. Now see, what is series combination of capacitor? First we'll see. If you want to call a combination of capacitor as a series, they must connect somehow like this. Look at this diagram. Like this they have to connect. Like this in the sense what? First, the second plate of a first capacitor, it is the capacitor C1 is the first. The second plate is this -1. Second plate of a first capacitor must be connected with first plate of second capacitor, right? So negative plate of capacitor 1 should be connected to positive plate of capacitor 2 and so on. See, in this capacitor 2, negative terminal of negative plate of capacitor 2 is connected to positive plate of capacitor 3. If the connection of capacitor is like this, then this system is called as a series combination of a capacitor. Series combination of capacitor. Now here you can see three capacitors C1, C2, C3. So your aim is to calculate total equivalent capacitance of all three capacitor. Total equivalent capacitance of all three capacitor. You can tell directly that if you want to calculate equivalent total capacitance, just add C1 plus C2 plus C3, right? No, it is a wrong actually. You cannot add directly. Why? You will see in this derivation now, right? Now in series combination of capacitor, charge is same or constant in all three capacitor. Why? See here, it is a battery. Battery is connected here, cell or something. From here charge will flow and same charge will flow throughout all these capacitor, right? Same charge will flow throughout all three capacitors C1, C2, C3. That's why charge is same on all three capacitor. So call that charge as a small q. Small q is the charge on all three capacitors C1, C2, C3. Now charge is same, then look for the potential difference. So potential difference of all three capacitors are the different here, right? Potential difference will be different for all three capacitor. Call for C1 capacitor, V1 is the potential. For C2 capacitor, V2 is the potential, and for C3 capacitor, V3 will be the potential. Now if you want to calculate total potential V, what you have to do? You have to add all those three, V1, V2, V3, right? So to get total potential of this combination, what you have to do? You have to sum up all different potential. That is V is equal to V1 plus V2 plus V3, right? This much everyone understood, right? So next, according to definition of capacitance, according to definitions of capacitance in previous video, what is that equation? C is equal to, don't confuse about that parallel plate capacitance, just look at the definitions of capacitance. C is equal to the ratio of magnitude of charge to the potential. So C is equal to Q divided by V was the formula, right? C is equal to Q divided by V. It is according to definitions of capacitance, right? Now from this equation, V is equal to, transfer this V this side and bring that C to the denominator. So from this equation, V is equal to Q divided by C, right? V is equal to Q divided by C. This much you know from the definitions of capacitance. So here it is, V is equal to charge divided by capacitance. This formula you know, right? Now apply this formula for all these three capacitors, right? So for this it is V1 is equal to Q divided by C1. Here it is, V1 is equal to Q divided by C1. Same here, V2 is equal to Q divided by C2. Q is common for all three capacitors, right? Now next, V3 is equal to Q divided by C3, right? Now substitute this all three value V1, V2, V3 in this equation. In this equation, what you will get? For V, it is Q divided by C, right? For V, for this V, it is Q divided by C. For V1, it is Q divided by C1. See here. For V, you have substituted Q divided by C. For V1, you substituted Q divided by C1. And for V2, you have substituted Q divided by C2 plus same, it is Q divided by C3. So you got equation like Q divided by C is equal to, so what you got equation? You got equation Q divided by C is equal to Q1 divided by C1 plus Q divided by C is equal to Q divided by C1 plus Q divided by C2 plus Q divided by C3. Now what you have to do? Here you have to take Q common. From this equation you have to take Q common, then that Q you have to transfer here, this side. What it becomes? It comes in the denominator, and this Q, the denominator Q will get cancels. What will remain afterwards? 1 divided by C is equal to 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3. Clear? What you have to do? From this equation you have to take Q common. If you got Q common, what it remains in the inside the bracket? 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3 will remain. The common Q you have to transfer left side of the is equal to sign. Here you have to transfer. That Q will come in the denominator, right? That equation becomes Q divided by Q into C. So Q get cancels. What will remain? 1 divided by C will remain. So final equation you will got as 1 divided by C is equal to 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3. So it is the final equation for total capacitance of a capacitor, right? Total capacitance of a capacitor connected in series combination. Clear? Now it is for 3 capacitor. Now suppose there are more than 3 capacitor, total n numbers of capacitor. Imagine total n numbers of capacitor. So what this equation becomes, 1 divided by C is equal to 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3, so on up to 1 divided by Cn, right? So in common way you can write it as using summation, right? 1 divided by C is equal to summations of I is equal to 1 to n 1 divided by Ci. So these both are the final equation for equivalent capacitance of a capacitor connected in series combination. Clear? Now some note point is total capacitance, in the sense equivalent capacitance of series combination is the less than the individual capacitance. Now imagine all these three capacitors have 2 farad value, then equivalent capacitance of series combination must be less than 2. It is the common point, it is a applied knowledge of this series combination capacitance. Clear? So this is of series combination. So in my next video we will discuss about parallel combination of capacitor. Thank you.